Now we're going to do something called projection. Again, we have our force F12 and F13. To project the force F13 on F12, we simply, of course, have the forces acting from the same initial point, and we draw a projection line from the tip of F1 perpendicular to F12. That's from F13 to F12. So this should be at a right angle. Then this distance here is called the magnitude of the projection, and this vector, which runs along F12 and has magnitude equal to the magnitude of the projection, is called our vector projection of F13 on F12. Now, vector projection of one force on another is not usually an important thing, but vector projection itself is, and since we have a couple of force vectors here, we're going to use those to illustrate vector projection. I'll comment that if this is a force and this is a displacement, then the vector projection becomes extremely important, and the dot product has a very clear interpretation as energy required to exert that force as the point of application moves along that displacement. Okay, well, that's all later in physics. I'm just pointing out that this idea of vector projection is very important and very powerful. Another way we could say this is that this vector projection is the component of F13 in the direction of F12. Now, the picture could get a little cluttered if I tried to do all this, but you can see that if I take this vector, the projection vector, turn it around and add it to the F13 vector, it brings us back to about here, and a vector from here to here is going to be perpendicular, turns out, to the F12 vector. And we then can say that we have the components of F13 parallel to the direction of F12 and perpendicular to the direction of F12. We're probably not going to do that right now, but it's also a very important thing. And also, if you happen to be also taking multivariable calculus, which a lot of you are, it's going to be a really important idea for you in that course as well. So, how do we calculate this projection? Well, this projection line along with part of this vector and this vector as the hypotenuse makes a right triangle. And this side is the adjacent side of a right triangle, which has this hypotenuse, so that this is just the magnitude. This distance is just equal to the hypotenuse, the magnitude of the vector, multiplied by the cosine of the angle. So our magnitude of our projection is 7.5 newtons times the cosine of 77 degrees. At least that's the magnitude of the projection in this case. If this vector was out in this direction where it had made more than a 90-degree angle, the cosine of the angle would be negative, and the projection would be in the negative direction relative to F12. And this thing would be, this quantity calculated would be for an angle greater than 90 degrees would be negative. So it doesn't affect this particular situation, but it's not a bad idea to put absolute value signs around that. Okay, well, in any case, now there's the magnitude of the projection. That's how long this vector, this projection vector, needs to be. The unit vector in the direction of this F12, you might recall, and if not, you can easily calculate it. Right there's our F12, is 0.67.74. So if we multiply this distance by a unit vector in this direction, or if we multiply the magnitude of this projection by the unit vector, we're going to get the vector projection. And the magnitude, of course, is this. We multiply that by the vector and so forth. Okay? So that's one way to calculate this. Now that relies on knowing that our angle here is 77 degrees. So there's a more general way to do it if we just know these components, and if we don't have any need to actually know the angle, if all we want to do is calculate the projection, that's actually quite easy to do, and we're going to do that here in a second. So here's another picture of our F12 and F13 vector with the projection vector indicated here, and the projection line right angle, and the angle theta, which we don't assume that we know. Let's assume that all we know is the components of F12 and F13. So now we want to arrive at some kind of a calculation scheme that allows us to calculate the projection. Well, let's observe that the projection is going to involve the magnitude of F13, which is just the magnitude of this vector, multiplied by the cosine of theta. Let's also observe that if theta is less than 90 degrees, that magnitude of F13 times the cosine of theta is going to be in the direction of F12, and if theta is greater than 90 degrees, it's going to be in the direction opposite F12. So that okay, now excuse that pause. I drew this green vector and this label in there, and I couldn't find the mouse. I might have been at a loss for words, but it was mainly I couldn't find the mouse. Okay, well, I've drawn this here, but now I've gone ahead and digressed down to this. So let me digress from here down to here, then I'll come back and explain this vector. This is just the unit vector in the direction of F12. Okay, this green vector. But I want to come down here and explain the scalar projection. And I'll note that I didn't have an arrow over this projection here. If this thing is a vector, then it's got to have an arrow over it. So it's vector projection of F12 and F13. Okay, well, the scalar projection is fairly simple to understand. You have this triangle and right angle here, which I haven't indicated, but that's understood. And the hypotenuse of this triangle is the magnitude of F13. Now, theta is the angle between this direction and the F13 vector. And the scalar projection is just the displacement from here to here. So the scalar projection is kind of almost like a displacement vector. And it's going to be equal to the magnitude of F13 multiplied by the cosine of theta. It's going to be positive if theta is less than 90 degrees, negative if theta is greater than 90 degrees. So it's just the length of this side, but also taking into account whether it goes this way in the direction of F12 or back this way in the direction opposite F12. So go back to our vector projection. Our vector projection is equal to our scalar projection multiplied by this unit vector. So let me write a couple of things in here. So once again, the scalar projection is just the length of this side of the triangle, except that it's negative if the angle is greater than 90 degrees and the vector is going to go back this way. Okay, we multiply that scalar projection, F13 cosine theta, by the unit vector in the direction of F12, and that gives us our vector projection. Now, we can calculate that in terms of the dot product. Of course, we know that the cosine of theta is the dot product, the dot product of the two vectors divided by the product of their magnitudes. And we can use that to come up with a fairly simple expression for all this. So I'm going to write that down, then we'll discuss it. I've just written down the same thing here that I had up here, except I've got this multiplication written as a dot, and in the context of dot product, it's best if I write that with an asterisk. Okay. So I've got this same thing written down here. This is the quantity that we're trying to compute. And here's the definition, or here's a relationship for the dot product, the standard relationship. Okay? Now, where do we see an F13 cosine theta, magnitude of F13 cosine theta? We see that right here. So we can write down that magnitude of F13 cosine theta equals F12 dot F13 divided by the magnitude of F13. You probably can't read that 3. And again, a bunch of things out that way I probably shouldn't. But okay, well, yeah, I mean, you can, and it should be F12 anyway. Okay, F12. Okay, that looks a lot like a 2. Okay, so we divide both sides by F12 in order to find F13 cosine theta. Yeah. Should use the word magnitude, but okay. So, well, that means then that this part of our expression becomes F12 dot F13 divided by the magnitude of F12. So we've taken care of this. What about our unit vector? Well, our unit vector is just what we get when we divide F12 by the magnitude of F12. It's a vector in the direction of F12. So that's multiplied by F12 divided by the magnitude of F12. And right there we have the calculation scheme for projecting one vector on another. All we have to do is calculate the magnitude of the vector on which we're projecting, which is our F12 vector, and take the dot product of the two vectors, which is, if we know the components of the vector, is a very straightforward calculation. And there we have it. Now, most textbooks, and for good reason, are going to collect this with this. So you have an F12 squared over here, and then you just have a number over here that you multiply by F12, your F12 vector. I really don't like that as a learning tool, although the formula is okay. You should understand what's going on. So you should understand that what we have here is basically the magnitude of the projection, except it might be negative if the angle is bigger than 90 degrees. In other words, our F13 cosine theta, this side of the triangle. And this is your unit vector. And you're multiplying that side of the triangle by your unit vector, with the consideration that that side of the triangle might go in the backwards direction. So this thing over here might be negative to indicate that. If you just mindlessly apply the formula, you have no connection with what's really going on here, and it's going to limit your understanding of the projection and of what you're doing and of how it might be useful in a given situation. So I recommend that you calculate this and you calculate this and test whether this is a unit vector. Then you can multiply the two and you can make sense. Of course, you should be thinking about the picture and whether the results make sense in terms of the picture anyway. One further picture to help put a point on what I just said. Here's your F13. I haven't labeled it, but it's the same picture we have here. The length of this side is the absolute value of this the hypotenuse times the cosine of theta. That's just basic trigonometry. So I got absolute value signs around magnitude of F13 cosine theta. And that, as you've seen, is equal to F12 dot F13 over magnitude of F12. You should continue to think about why that's so. Put absolute value signs around that. So this has a meaning and this has a meaning, and you should think in terms of those meanings.